everybody, welcome to the last video in our quadratic section. This is lesson number 7, where we'll talk about all of the applications, so all the word problems to this. And you know, all of the other ways we've seen that you can solve a quadratic equation are still true here. That some of the points now are just going to have a meaning, right? There's going to be a context applied where if, for example, we're looking for a vertex, that is like the maximum point or minimum point on our graph. Now, those coordinates actually mean something with respect to the question, right? Those variables are going to have a context, so it actually matters, you know, which point we're actually looking for, and that's going to depend on the context to the question. So, all the information at the top here really is just information that we've seen over the past 6 lessons, right? It just kind of puts it all together in one spot. So we've talked about x-intercepts, we've talked about zeros, we've talked about factoring, we've talked about, you know, an axis of symmetry, how to solve a quadratic equation, either using a graph, using, you know, those algebraic methods that we started to see in the last few videos, and, you know, the quadratic formula, the one we did in the last one, so that we have a whole bunch of different ways to solve one of these problems. And the challenge is it really doesn't tell you, you know, what you're looking for, right? It really doesn't tell you how to find that point that you really care about. So we'll do a few different types of questions here. There is a wide variety of these applications, and, you know, once you've done a couple of them, they all start to seem quite similar. There are commonalities between them for sure. So if we take a look at the first one, we've got a rectangular lot bordered on one side by a stream, the other 3 sides by 40 meters of fence, and the area of that lot is a maximum. We are asked to represent the area of that lot as a quadratic function. A is going to represent area, x represents the length of one side of that lot. Okay, so function is a key word to this, and I know that the two things I need to use in my function, a is the name of it, x is going to be the input. So I know in function notation, this is what this will look like. Typically, you see this as y. Okay, but we're going to use function notation to do this. I'm also told a couple other pieces of information. I know that this is supposed to be a maximum, and that word, as soon as you see it, should be synonymous with vertex, right? I know I'm looking for the maximum point on my graph. In other words, I'm looking for the vertex of it. Now, I am given a picture here to help, and I'm told that, you know, I've got 40 meters of fence to use. 3 sides are what I have to actually put that fence on, because the river or the stream acts as the border for the other side. So I only have to account for 3 of them. Now, the side lengths are different, right? It's a rectangle, and I know that 2 of them are going to be the same. Now, x represents the length of one side of this, so if I make a choice here to label either the width or the length as x, well, I'm just going to label the length as x, and we'll call the widths y, some other dimension that I don't know, and I don't know how they are related to my length, so I have to call them something completely different, right? I have no information on what the width happens to be. Now, I do know there are 2 things that I can use as part of a rectangle, right? Area is one, but perimeter is the other, and that 40 meters of fence is really a perimeter, right? It goes around the outside of this rectangle. So I can start by representing an equation for perimeter, since I have a number for it, right? Perimeter is going to be 2 lengths plus 2 widths, so 40 is going to equal, well, here I don't really have 2 lengths to think about, right? I only really have 1, so this is just going to be length plus 2 widths, right? I'm told again that the stream borders one of those sides, so I don't have to use that one, so I'm only going to use 1 length represented as x to do this. So 40 is equal to x plus 2 y's, right? The y's are representing the width. So I've got, you know, an expression for perimeter decided on. Now, the other thing to think about here is I need to represent this, you know, the area as a quadratic function. And the reason why it's worded that way is because if I think about the area of a rectangle as being length multiplied by width, well, I have 2 different variables here, x times y. So the area x times y instead. But that's, confusing because I have an area as a variable. I don't know what the area is. X, I don't know the length. Y, I don't know the width. So I have three unknowns, no numbers. That is a problem for us to go and evaluate. So what we're going to do is we're going to use our perimeter equation that we came up with, 40 equals x plus 2y, and we can rearrange it to solve for one of my two variables, either x or y. And by doing so, I can represent that in my purple equation because those variables mean the same thing, right? The x's in the blue and purple equations both represent length, and the y's in both of them, well, they both represent width. So it doesn't really matter which equation I use. Right, I am asked to represent the area as a function, so I'm going to need to use the purple one here, but I can use the blue one to help. So with that 40 equals x plus 2y, if I were to just rearrange it and isolate for x instead, well, this would now say x is equal to 2y minus 40. All right, all I did was subtract that 40 on both sides of that equal sign. But now if I know that x is equal to 2y minus 40, well, that should be the same thing as x in the purple one. So I'm going to take out x and put in, 2y minus 40. Ooh, should I do this? Yeah, I already started, so let's do this, and then I'll show you the other way to do this as well. So let's put in x just like I said I would. So into that area equation. So area is now a function of x. Oh, wait, sorry. No, area equals, take out x, put in what it's equal to, so that's 2y minus 40 multiplied by the y that is still there, right? X is this expression in the brackets that was in blue. The other y still remains. So this is now actually a function of y because y is the only variable present. And if I actually just distribute into the brackets, well, I'd get this expression, area as a function of y is equal to 2y squared minus 40y. Okay, so I've represented this area as a function of its width. Right, I've basically replaced the length with an expression. Now, if I do this the other way, so the whole reason I chose to do it this way in the first place is to avoid, dividing and avoid the fraction. But the only difference is I'm going to have 1/2 in front of my x when I isolate it. So I could do it this way, or if I solve this perimeter equation for y instead, and I'll show you what it looks like right from this same point. So 40 equals x plus 2y. So let's say instead we actually solve this for y. So if I subtract x on both sides, 40 minus x equals to 2y. But if I divide everything by 2, I get 20 minus 1/2 x equal to y. I can still do the same thing and replace it in my area equation if it's still area equals xy. So that means area is going to equal, this time x stays, and we're going to replace y with 20 minus 1/2 x. Right? The same sort of deal, but replacing the other letter. And now this will leave me in a place where area is a function of x, which will equal negative 1/2 x squared plus 20x. So there are two ways to do this, and the choice you make really doesn't matter. It just defines your variables differently when we go to graph this. Okay, so the choice you make is irrelevant. And I know the equations look very different. One has y's, one has x's, but when you go to graph them, what you'll find is, you'll find the area, that's the vertex, the maximum, but the other number attached to it, and we'll graph this, I'll show you, it'll be different depending on the variable you choose to start with. So let's go try to graph this. And I'm going to grab my calculator here, and we'll graph the one that we started with. So we'll graph the purple one, just because it's a little bit easier to put in the calculator, and we'll see what happens here. So hit our y equals button, and that's where we're going to put in 2y squared. But the problem is we need to remember that when I graph in my calculator, I'm really hitting the button for x. So it's going to be a little bit confusing because the letters are backwards, right? But really just pretend that this x is representing y. Okay, that's all this is saying. Now when I hit graph, I don't think I'm going to see anything because of the size of the numbers, right? And let me make sure that I've done my subtraction correctly here, because I should have, oh, I did, okay. And I think that's my 2y. I'm solving for x, so that's 40 minus 2y. That's why my sign is a little backwards here. So I need to actually alter this. That's why it doesn't work for me. So let's fix my subtraction up. So if I get x by itself, I'm subtracting the 2y's on both sides, so this should be 40 minus 2y, which will change my equation to being negative 2y plus 40y instead. That's why. My signs are backwards. Okay, so I'm just going to fix up this purple one here. So that should be 40 minus 2y. So that looks much better. I got my 40y's are positive, my 2y's negative. That makes a lot more sense. Okay, sorry about that. Let's try this again. So negative 2, and I'm going to hit x, but remember that it's actually y. So plus my 40x again, graph. And I'm still not going to see anything, but now the line goes the way it's supposed to. Because I know if this is a maximum, it should open downwards, so my vertex should be at the top. So I need to adjust my window here. I don't know how far up I have to go, so I'm going to press zoom. And option number 0, if you scroll down, says zoom fit, so I can fit this right onto the screen and adjust from there. So I know this gives me a good starting point. So I know there's my vertex somewhere up and to the right. So window. We got to go right a little bit more, so let's make our x maximum. I'm going to double it, make it 20. Let's see where that gets me. Okay, so my vertex is right at the top, so it'll give us a little bit of room to work with. So y maximum, instead of 200, I'll make it 250. And there it gives me enough room to work with. So I know what my graph will look like now, so I can just have a little sketch of it on here. So if that's my origin, really this is going to look something like this, right? And I don't need it to be perfect, I don't need to label it or anything, that's just shape of it, right? As a maximum, I'm looking for this vertex. Okay, so I've got part B taken care of, there's my graph. Now for part C, what dimensions provide the maximum area for this lot? Now here's where I can actually use my calculator to help. So we're going to go find the vertex. So we'll hit second trace maximum. Something that we've done before. So second trace maximum. And then we'll do the left boundary, the right boundary, and then we'll hit enter again. So define where your calculator is going to search. So on the left side of the vertex, hit enter. Move it over to the right side of the vertex, so keep going just till you're on the right of it. Doesn't really matter how far, there's no specific point, just on the right side of that vertex. So hit enter again. My calculator will search in between, and here's what these coordinates are going to tell me. So the actual vertex is at 10, 200. Now you might be thinking that, hey, I've done, my vertex tells me my x, my vertex tells me my y, because a coordinate pair is x, y. And that would totally make sense. But here, since there's a word problem and it's a context attached to this, I really have to remember what I've just graphed, right? So this vertex came from graphing this function, area with the input of y. Okay, so this was the input value into that equation. This was the output. And in terms of a coordinate pair, if it's x comma y, x, the number in that place is our input, and the number in the y place is our output. So in terms of what we've just found together, the input value here, right, is y. And we said that y is going to represent the width for us. Right? The variables are defined very specifically as being length and width. But the output is actually the area, not the other dimension to the rectangle. So I know that if 10 is the width, and 200 is the area, well, if the area is equal to length times width, then I know that 200 should be equal to length multiplied by 10. And if I divide both sides by 10, Now I know that the length is 20. Right, which makes sense. So in terms of my dimensions, I've got 20 and 10 for length and width, respectively. Because if I look back at this original shape, right, that original rectangle, I had one length of x, which is 20. I had two lengths of y, which are 10. And if I add those up, my perimeter is 40. So this does work, and this is the biggest possible rectangle I can make. It'll have an area of 200. Okay, so these area types of problems are one of the most complicated because of the way that you would graph this. And I can graph the other one too, and we'll see what happens. So if I actually graph this green one, y equals instead, take out this equation, put in negative 1/2 x squared plus 20x. And I hit graph, the shape of this graph will relatively be the same, but the vertex will be a little different, right? Because I've changed the equation. So window, I got to go right. So x max is at 20. Let's make it 35. It just gives me some room to work with. So there's my vertex. Let's go find it. Second trace maximum. And I think you might already see where this is going. My purple maximum had an x coordinate of 10. So my green one, right, this other equation, should tell me that the x coordinate's 20. Which, there you go, there it is, right? The x coordinate of 20, which would be my length instead of my width, but the area is still 200, right? That should be the same. So it just will give you the other dimension, depending on the formula that you choose to work with. Okay, so it really doesn't matter which one you choose, it'll just give you the other variable instead. Okay, so there's your area example. Second one here, we'll talk about, actually selling something in terms of profits and revenues. So a restaurant's currently selling some burgers for $6. From previous sales, they know that if it's $6 a burger, they can sell 120 of them. After doing some research, they discover that for every time they raise that price by $1, they're going to sell 10 less burgers, which makes sense. You make something more expensive, less people are willing to buy it. What should the restaurant charge if they want to make the most amount of money? They want to make the most profit. That's the whole point of the business. Now, when working with revenue functions, you got to define your variable here. Now, there's always two things that could happen. Either you change the price and it goes up, or you change the price and it goes down, right? But the number of times you change that price, that's what we really care about. So, and that's the thing that's always going to change. So we're going to let x be the number of price increases. And I know I want it to be price increases here because it says straight up in the question that it's a price increase. Right? I'm increasing that dollar amount. Now in terms of, revenues and profits, revenue is the total amount of money that you would bring in. Right? Not accounting for any deductions or any profits, anything like that, just the total amount of money. So for revenue, we want to figure out what that function will be for this company to bring in the most amount of money possible. Because usually when your revenue is as high as possible, that means your profits are as high as possible as well. So we're making that assumption here. So we've defined a variable, but now we've got to represent the selling price of each burger. And if I look at what the original price happens to be, it's $6, right? That's the original. But if I include the change in there as well, I know that if I change the price once, I'm changing it by $1. So I'm going to have to add my variable to this. Remember, x represents the number of price increases, and really this is just 1x because the dollar amount is 1. So if I change the price one time, this function, this expression will now say 6 plus 1. So my new selling price is $7 because I've increased it by 1. Now if I change the price twice, that means the price goes up by $2. My new price is $8. So you can see how this works if I keep the pattern going. And if I represent the number of burgers sold as a function of the selling price, well, the number of burgers I'm selling originally is 120. Right? So no price change is 120 burgers. But as I change that price, the number of burgers sold goes down. So there is a decrease here of 10 every time we change the price. So the variable is going to be the same in both. It's going to be x. And because it represents a price change, the coefficients are going to tell us how much that change is going to be. So in terms of the number sold, I'm going down 10 every time we increase. In terms of the price, we raise it $1 every time we increase. Now, a revenue function is the number sold multiplied by the price. If I sold 1,000 pencils at $1 a piece, well, my revenue is 1,000 times 1, which will give me $1,000. So if I represent this revenue, so my revenue function is revenue with the input of x, which is my price, so 6 plus x, multiplied by the number sold, 120 minus 10x. There is my revenue function. Right? I don't have to really multiply them out and distribute and collect like terms. You absolutely can, but your calculator takes care of that step for you. So no need whatsoever. If we're going to find out what selling price provides this maximum revenue, well, we can use a little bit of a chart to help. I can show you how to do this on your calculator as well. But let's think about this in terms of this chart here for a second. So if I make one increase, the selling price changes to $7. The number sold goes down to 110, and I can grab my calculator to help out here. So that's be 770. But if I change it 2 times, well, the new price for a burger is going to be $8, but the number sold will drop by 10 more down to 100, but I'm making more money, right? Even though I'm selling less, the price went up, which meant I got more money in total. So I still went higher, so I got to find the point where it's as high as possible. So let's talk about $3 this time. Now my new price is 9. I'm only going to sell 90 burgers, but that will still bring in more money, $810. Okay, 9 times 9 is 81, so 810. What about 4? Well, my new price is $10. This will take me down to 80 burgers sold, but you can see now the revenue has dropped. It's down back to 800. So $810 in revenue is the most I can bring in if I charge $9 per burger. So the selling price that provides that maximum is $9, and the maximum revenue is $810. Okay, so this example makes a little bit more sense in terms of dollars and people and selling things. But if I go to graph this, well, I'm going to put this expression in just like it says. So 6 plus x in the first set of brackets, 120 minus 10x in the other set, hit graph. And again, you probably won't see too much. This is actually super helpful. So I know it doesn't go high up enough. So window, y maximum is only 250. Let's make it 1,000. So I got a vertex, and again, that key word is there. It says maximum, so second trace maximum. We're gonna go find the vertex again. Left bound, right bound, enter, just like before. So let's say left bound of the vertex, right boundary on the other side. Enter, enter. So there you go. Now I know my y is gonna say 810, but x says 3 this time. It doesn't actually tell me the dollar amount. So it says 3 because that is the number of increases required, right? That's how we defined our variable, right? So if you actually do this in the calculator, you will find a vertex of 3 and 810. In terms of this question, 3 is the number of increases, and 810 is the revenue. Right, so all of the same things are true, right? There's my number of increases, and I have to work backwards again to find out what the actual selling price is. But if I know x is 3, 6 plus x would give me 9 anyways, so I can still do it. And my revenue is 810. So let's try this again, maybe without the chart. Okay, so John's selling cotton candy, maximizing revenue, determines that the price of candy, if he decreases it by 25 cents a bag, he'll sell 25 more bags each day. Currently sells 300 bags at $5.50 a piece. Use a graphical approach. So we'll use our calculator to solve this. So number of bags sold as a number of price decreases. So that's my variable defined for me already. X is the number of decreases to that price. Okay, so number of bags sold. Currently we're selling 300. And if we decrease the price, we're going to sell 25 more bags. Okay, so all that stuff will go together. All the physical amount of items go together. All the pricing information goes together. So current price is $5.50, and we're decreasing it by 25 cents. So current price $5.50, and we're decreasing it by 25 cents every time. So there are my two expressions. So my revenue in terms of x is the price multiplied by the amount. So 550 minus 0.25x multiplied by 300 plus 25x. And the order you make those brackets doesn't matter, right? For multiplication, the order is irrelevant. So I've got my expression. Now I'm just going to graph it. Okay, so y equals, clear it out, brackets, $5.50 minus 0.25x. So 300 plus 25x, close it, and then graph. And I don't know if I'm going to see too much. Okay, so with the way my window settings were, I know my vertex is right up at the top, and I know this is a maximum because it opens downwards, right? My vertex should be the highest, so window, our y maximum isn't enough, so let's double it to 2,000. And again, I'm really just guessing. I don't know where these numbers happen to be. So it is somewhere up here. So second trace, maximum again, same questions, left bound, right bound, enter. So you can see how repetitive they start to get with regards to what you're looking for, right? You're really looking for a maximum every single time. So go far enough over so you're on the right side of your vertex, enter, enter. Here is our vertex. Okay, so we got a vertex at, I can round this up to 5. So 5 at 1806.25. So with regards to that number, this is the number of price changes. This number is the revenue. So the maximum revenue is $1,806.25. And the number of price decreases is 5. So we're looking for a selling price here. So we actually have to go find that. So price. We made an expression for price that said it was $5.50 minus 0.25x. I know x is 5. So 5.50 minus 0.25 multiplied with 5 for our selling price. And this 5 is the one from the vertex. Okay, that's where that comes from, the number of price changes. So 550 minus $1.25, I believe, yeah, 0.255. So $4.25 is what this person will charge for that cotton candy, right? Or they'll decrease the price enough to make sure they get their maximum revenue. So the revenue questions are very, very, very similar. Either you go up in price or down, and the resulting number you sell changes as a result. So as one factor increases with the positive, the other one must decrease with the negative to account for that supply and demand situation. Okay, 4, 5, 6 are very, very, very similar. So let's just do one of them here, and I'll let you try the other ones. They're basically the same question. So example 4, path of the water slide is modeled by this quadratic equation. H is the height above the surface of the water. D is the horizontal distance they slide, what they travel, measured in feet. Algebraically find the horizontal distance Aisha travels before dropping into the pool. Okay, so you gotta think about the situation. So let's draw this out. Just some axes for us. So here's y, here's x. And, if it's a water slide, the path of the water slide modeled by that, okay. So we're going down, and here's the water underneath, right? If it's a water slide. So I suppose like the ladder would be off on the side, right? Like you would climb up the ladder till you get to the top, and they would sit down on the slide, and down we go. So we're really just talking about the path of the slide where you slide down, not the ladder going up. But you can see how it would look, and we're really looking for where they hit the water, right? So we're looking for this point right at the bottom. And if you remember what that would be called, this is a 0. So really, all I'm asked to do is solve this equation. That's really all this says. So the height as a function of distance traveled is equal to negative d squared minus d plus 12. And if I'm asked to solve this, really I want the height to be 0, right? Water level. So minus d squared minus d plus 12. Really this is a factoring question, because if I can factor this, I can solve it. So Let's take out a factor of -1 to make this d squared plus d minus 12. So using that sum and product method, I'm going to look for two numbers that multiply together to give me 12 but add to 1. So 4 and 3 are able to do this. So let's do d plus 4 and d minus 3 to be able to factor it. And that should add up to 1 multiplied to -12. It looks good. So if I actually take each of those factors and solve for 0, d plus 4 equals 0. So that means the distance traveled could be -4, or d minus 3 equals 0. So d is actually equal to 3. Now only one of these makes sense. Now I can't really travel a negative distance. That would mean I'm going backwards. So I can't take the -4. So d must be 3. Right? That number right there is 3. That's my x-intercept, my 0. So I'm done. So she's traveled 3 feet before dropping into the pool. Okay, there we go. So the number you find actually has to fit in the context, right? It has to make sense. I know there's two solutions to this equation, but one of them doesn't make sense with the context. So you can try the other ones as well, you know, and it doesn't say how to solve this. So you could factor it, you could use the quadratic formula, you could use decomposition as a method of factoring. It really doesn't matter. But really all you're going to do here is solve them. That really is all you're asked to do. So the last one we'll talk about then before we wrap this whole lesson up is, you know, another area one. So the area of this table is 45 feet squared. The length is 4 feet more than the width. Algebraically find those dimensions. So we won't graph this one. So let's just draw this out. Ping pong table is rectangular in shape. I'm told the area this time is 45 feet squared. The one we started with in this lesson didn't tell me the area. I had to find the maximum. So I know it's 45 feet squared now. And I know the length is 4 feet bigger than whatever the width is. So if I label the width as W, I know the length should be 4 more than that. So W plus 4. Now if I'm going to do area here, well, area is the same thing as saying length multiplied by width. So area is equal to, well, the length is width plus 4, and, well, the width is just width. So if I actually multiply these out, and I'm going to get area is equal to W squared plus 4W. But I know the actual area is 45, so I can put that into the equation as well. So this is super, super good. We're in a good place right now. If I'm trying to find the dimensions, I really am trying to solve a quadratic equation. And every time I go to solve one, it should be equal to 0. So let's subtract 45 from both sides to make that happen. So I'm going to try to solve the equation. 0 equals W squared plus 4W minus 45. And if I try to factor that, find two numbers that multiply to 45. So add it to the top. So multiply to -45, but add to 4, 9 and 5 will be able to do that for us. 9 times 5 is 45. So 0 equals W plus 9 and W minus 5. That'll add to my positive 4. That'll multiply to my -45. So W plus 9 equals to 0, which means the width must be -9. Weird. Or the width must be 5. Which makes a lot more sense, right? If it's a dimension to something, you can't have a negative. So if the width is 5, the length is 4 more than that. The length must be 9. Right? Must be positive 9. So I found those dimensions relatively easily just by setting up an equation that you can factor. Right? So there is everything that we've talked about in quadratics kind of wrapped up into, you know, one question. It talks about a vertex, talks about factoring, a maximum, all of those things start to come together with these types of problems. So like I said, I left the other two in there blanks. So you can check that solution key. I'll have them in there for you. But this brings us to the end of our quadratic section. You know, you can find some of the other lessons in there as well, other units. We're going to have some statistics, measurements, trigonometry stuff all over the place. I'm not sure what order you're watching this in. But all those things will be there as well. So I hope you found this helpful. If you did, drop a like, leave a comment, something like that. but we'll see you in one of our next units. Maybe you'll see this in 20-1 course as well. So until next time, take care, and we'll see you next time.